Hello, and this is a video about how you can use Lua Coroutines to automate things in your games. And by things I mean cut sequences, moving platforms, tutorials, user interface dialogue sessions, that sort of thing. In a way, this is a continuation of my first video, which was embedding Lua in C++, and you can watch that video from the link below. And I do recommend that you watch it before seeing this one. I'm outside today because the heat has driven me back into my primal form as a metalhead. I can't be inside today, it's just too hot. So let's just get on with it.
I'm going to start this project with a skeleton pixel game engine application that already loads the Lua virtual machine. Here we can see we're including the necessary files for Lua. Here is the function we created in the first part of this series, check Lua, which is a convenience function to check for error messages when we do calls to the Lua virtual machine. And here is the class overriding the pixel game engine. Already I've created an instance of Lua called script. I've loaded up some graphics here, which is just a simple tile set to make things a bit more visually pleasing. I load that graphic in onUserCreate, and in onUserCreate I also define my Lua virtual machine and give it the libraries necessary. In this case I'm giving it all of the libraries. I then look for a file called automation1.lua, which is the script file we'll be using for the start of this video, and that's all it does. It's a 512 by 480 pixel game engine where each in-game pixel is 2 by 2 screen pixels. And if you're looking at this and thinking, whoa, slow down a little bit, Javid, then I do urge you to go and watch the video Embedding Lua in C++ Part 1. It covers all of the basic syntax and the methods required to transact information between a Lua virtual machine and a C++ environment. But if you can't be bothered doing that, don't worry. I think Lua is semantically simple enough and self-describing that you should be able to follow this video if you've got a basic level of programming knowledge.
Now, in that video, we used Lua in a very simplistic form. It was essentially just a glorified configuration file, and the transactions we did between Lua and the C++ environments were quite minimal.
Now, because the first video was so simple, I thought it might be useful to show a Lua script loading up a tile-based level. So I'm going to open up my automation1.lua file and start coding some Lua. I'm going to create a function called loadLevel. And this function takes two arguments. The first is host, and the second is going to be an identifier for a specific level in your game. This host variable is quite interesting. You may notice that this function loadLevel doesn't necessarily return anything. In fact, it's going to call the host application in C++ to construct the level on Lua's behalf. As with most things in Lua, there are 1,000,001 ways to skin a cat. And so I'll reuse the disclaimer I made last time that this is the way I do things. It's not necessarily the best way or the most optimal way, but I find it a way that's easy to debug and easy to extend. The way that Lua is implemented in C imposes some quirkiness regarding how we can call functions in the host environment. But just bear with me for a few moments whilst we work through this, and the nature of this host variable should become self-explanatory. I'm going to create two variables, map, which is going to be a string, and size, which is a Lua table containing a width and a height. Don't forget, in Lua, pretty much everything is a key value pair, so here we're effectively describing something analogous to a struct. Then I'm going to check the value of the level parameter that we pass in, and respond by creating an appropriate map for that level. Now, this is how I do things. And this isn't necessarily the best way to represent level information. I'm using ASCII here because it's convenient and flexible enough for me to make this video. Typically, in level design and layouts, you will want a more sophisticated representation for your level. But in effect, all I have are tiles that exist and tiles that don't. You've seen me use this approach in countless videos before. One of the nice things about this being Lua is you have access to all of the additional Lua libraries and functions. So you could open up additional files, you could read from them and parse them in an appropriate way to extract the level information you need. In fact, popular tile-based level editors such as Tiled will even output the level descriptions as a Lua script, so you could call that directly to construct the required information you need, and then you can parse it appropriately. But for now, I'm just sticking with a string. And the string is 16 characters wide by 15 characters tall. You'll notice the concatenation dots at the end of the string, which allow me to graphically describe the level in text. My C++ host program has no notion of what is the level at this moment, so we'll create a function in C++ and call it with the dimensions of our map. So when I prefix a function in Lua with an underscore like this means I'm going to be calling a function in my C++ host environment. This is a JavidX9 convention, and you'll see I'm passing back to my host the host variable and the size, width and height. Going back to C++, in the onUserCreate function, I'm calling the doFile function, which is executing the script. In terms of execution, our script currently doesn't do anything. It simply defines a function called loadLevel, but it still needs to be executed with the doFile function, if for no other reason than to define what the loadLevel function is. So we can call it, which is exactly what I want to do now. So I'm going to get the global loadLevel, the name of our function in the Lua script, which if you recall from the previous video, we'll place back on the Lua stack some callable index that represents that function. We needed to pass two parameters to our loadLevel Lua function. The first was this odd host parameter. And what I'm going to do is call the Lua push light user data, which effectively means push a pointer. I'm including the Lua virtual machine, and the pointer I'm passing is this. As we'll see in a moment, and maybe you can recall from the previous video, that when Lua calls a host C++ function, those functions are defined statically. It doesn't really know what object they belong to, and we're calling these functions from an object that we've created. In this case, it's GameWorld, a subtype of the Pixel game engine. It could well be that we have many different objects, each with their own unique Lua virtual machines, but there can only exist one host C++ function that it can call. We can use this variable, or the host variable in the Lua script, to discriminate between the source objects that are calling the functions in the first place. The second argument of our loadLevel function was the level identifier itself, and for this video there's only going to be the one level, and it's going to exist at index 1. We'll call the loadLevel function using the Lua pcall function, and if all's well, that'll return true, successfully finishing onUserCreate for us. If we had syntax errors in our Lua script, they would have been caught by these check Lua functions and displayed in the console. Our Lua script is going to call this createLevel function as part of the hosts API. So let's create that. Because I want this video to be somewhat informative, I'm going to be doing quite simple things in an overly verbose way. And I'm doing this because I hope it gives you some inspiration as to how you can represent things that are more complex using very similar techniques. The level is going to be defined as an array of tiles. And for now, I'm going to represent those as tile types, empty or solid. That's all I've got for this demonstration. And I'm simply going to use a vector to store the tiles themselves in a variable called vLevel. I'm also going to store the dimensions of the level as well. Somewhere in my game class, I'm going to create a function called createLevel, which takes in a width and a height. And it sets our level size vector accordingly, clears out anything that may be existing already, and allocates enough space in our vector to store all of the elements of the tile map. Lua itself can't see this createLevel function directly, nor can it call it either, because this is a member function of a class, and as you can see here, contains nothing to do with Lua at all. I'm going to create a wrapper function instead. Now there are lots of third-party libraries which you can use, which use various types of template black magic to do all of this for you, but again I'm trying to be verbose and doing this by hand. So I'm going to create a static wrapper function, which is the one that Lua will be able to see, and I'm prefixing that with wrap. Now recall from the first video that these functions need to return an integer, and they take in the Lua state. Throughout this video I will be omitting lots and lots of error checking, which you should really do when you're working with external scripts to make sure nobody is trying to hack your system. But at a very basic level, the first thing I'll do is make sure that when Lua has called this function, it has provided 3 arguments on the stack. If we look at the script, we're expecting it to return the host, the size width, and the size height. On its own, this error check is completely insufficient. It doesn't notify the user of anything, nor does it get the system into a known safe state. So when you're doing this seriously, you'll probably really want to think about how you handle errors. This function is declared as static, so it's the same function in any instances of this class. Therefore, I can't simply call the createLevel function I've just defined, because that createLevel function belongs to a particular class. Though I can now work out quite easily which class it belongs to, because the first object provided on the Lua stack was the pointer to this object. So this has been transferred to Lua via the load level function, and when we communicate back with the host in our create level function, we send that pointer back. Therefore, when I extract that pointer from the Lua stack, I can cast it to a game world object, and it will be this game world object. I'll also get the width and the height required, and now I can call the create level function relative to this object with the width and height parameters. All being well, I can return 0, which means I'm not returning any information back to Lua. Just to make sure that this relationship is working, I'm going to run to cursor using the Visual Studio debugger to this line here, which will only be called if our Lua script has successfully moved the pointer around as necessary. So I'll press Ctrl and F10 here. Oh, and it's just closed. Something's gone wrong. Well, let's see if any of our Lua calls failed. So instead, I'm going to run the debugger to here so I can interrogate what the error messages might be. And indeed, there is an error message, and if I put my cursor over it, it says automation1.lua line 27 attempt to call a nil value global _ create level, i.e. it doesn't know what this function is. And indeed it doesn't, we've not told it. So here I'm going to use the Lua register function to register the name of our host function, _ create level, and bind it to the wrap create level static function as part of our class. So let's try this again. I'm going to try and run the debugger to this line here. This looks a bit more promising. So this function has been called via our wrapper for the correct object, and the arguments passed in are 16 and 15. Very good. That's now defined the vector that's going to hold all of the tiles in our level.
Now, this back and forth relationship between Lua and C++ is just something we have to get used to, but having the wrapper functions there gives us a chance to perform some degree of error checking and sanitization of the inputs Lua is providing to C.
Now, as I mentioned before, I'm doing a very simple thing, but I'm doing it in a verbose way. And so here I'm going to allow Lua to physically construct the level in our game engine tile by tile by using two nested for loops. To iterate through all of the cells in our string, extract the character for a particular location, and yes, you'll have to deal with stuff like this in Lua because Lua counts from 1 and not 0. I'm sure that was a good idea to somebody, but not to most programmers. But what we should see are some familiar one-lone coder staples, y times width plus x. The offset of starting from 1 does upset that a little bit, you just have to deal with it. But we can check that if the character is a period symbol, then we're going to send through an empty tile, and if it is a hash symbol, we're going to send through a solid tile, or a block in this case. And we can also pass along the coordinate. This requires the definition of a few more things. Firstly, tile empty and tile block. Well, I'm just going to define those at the top of my Lua file as being 0 and 1. In the C++ file, this ties into the enum class type. Secondly, you'll see that we've got another host function here, _setTile, which means we need to go back to the C++ and provide this setTile implementation. Firstly, I'll create a member function of the class setTile, which takes in the position and an identifier for the tile. This will be an identifier in an integer format from Lua, so I'm going to convert that to the necessary enum class type. Yes, I could use casting to do the same thing, but again, I'm going back to this excuse or reasoning that keeping it simple and verbose may be more beneficial for you guys. And given the coordinates that are returned from Lua, I index my vector appropriately and set the tile appropriately. Just as before, I'm going to need a wrapper function, which is the one Lua actually calls. I can take this opportunity to do some very basic error checking. The first object returned is always going to be, and this is just my protocol, this is how I'm implementing these things, it's going to be the pointer to this object. Then it's going to be the coordinates and the tile ID itself, and with that information, I can call my setTile function. Just as an aside, let's say some of this information was invalid. Well, my setTile function could return as such, saying it's invalid, and I could then implement code here which pushes the results back onto the Lua stack. So we could wrap this in some sort of error checking in Lua itself. We mustn't forget, again, to provide access to our wrapped function by registering it with the Lua virtual machine. And I will stand by my claim that last time this was omitted on purpose to extract the full educational benefit from debugging it. I definitely didn't just forget. But anyway, now we've started to fill our vector of tiles with tile information, we're going to need to draw these tiles to the screen. I'll start by just clearing the whole screen to cyan. And I'll create a little 2D integer vector to iterate through all of the tiles in the vector, using 2 nested for loops. By now, the tile vector has been populated with solid or empty tiles, and we also know what the size of the level is too. I'll extract which particular tile we're drawing in this instance, and then draw it. If the tile is declared as empty, I'm not going to do anything. If it's declared as solid, I'm going to use the Pixel Game Engine's draw partial sprite function to draw a block sprite kindly provided by Tutus on the Discord server in the correct location. So let's take a look. And very nicely, we can see a graphical representation of the level we defined in ASCII in the externalized Lua script file. One of the benefits of scripting is we can easily make changes. So if I add in 3 blocks up here, I don't need to recompile anything, I just run the program and we see our 3 blocks have appeared.
It can be argued that reducing compile times is one of the primary reasons you would want to go to an external scripting language, as well as sort of modification and that sort of thing. The projects I show on this channel are quite simple and thus compile very quickly, but as your projects grow in sophistication and complexity, the compile times will grow too. And it gets quite frustrating if you just want to make a very simple change but have to wait 20 minutes at a time, or even longer maybe, for such a small change to be effected.
Adding external scripting to your application is something that needs to be designed, and it needs to be thought about from day 0 of creating your application. It's very difficult to shoehorn in external scripting later on. So I would recommend that even if you don't know yet if you're going to need scripting but you think you might, do start leaving some stubs and some functions hanging around, or compartmentalize your application in such a way that it is easy to mix with a scripting language such as Lua later on. And this is no easy task, and does require a bit of thought and some design decisions to be made. One approach people often go with is to have a very small part of their application written in C++ and the rest of it written in Lua. For example, you might just use the C++ for the rendering part. And everything else, including user input and the game loop, exists in Lua. A natural extension of that might actually be to put the game loop in C++. So let's get some input here, and we have that in a loop. And for every frame of our rendering loop, we call Lua, some sort of update function. And with this update function, we pass the equivalent of our felapsed time, or delta time between frames, and we use Lua to update every single object. So the position of an object, we do all of the kinematics and velocity stuff, all of the collision detection, and everything else happens in Lua. We just simply use C++ to do the input and the rendering. I don't particularly endorse this way. In some situations it is the right way, but it relies a lot on Lua doing the hard work. And Lua, although very flexible and really easy to use, isn't the fastest language in the world. It's no slouch, but it's nowhere near as fast as just raw C++ doing these things. Every frame we need to call Lua, and every frame we need Lua to run its interpreter and its just-in-time compiled stuff to perform all of the physics updates and game updates and everything else. So really all of the critical, crucial stuff is happening in the slower domain of the two we've got available to us. There's also a considerable overhead in calling Lua frequently. Let's say we lent on C++ a little bit more to handle all of our objects. Well, nothing's really changed. We still need to call an update function for all of the objects in the game and update their positions. In fact, potentially this situation could even be worse because we've got a lot more transactions between the C++ domain and the Lua domain. So we've got a lot more stack manipulations to worry about and a lot more error checking to perform. The other extreme, of course, is to have everything in C++ and very rarely do any transactions with Lua. And this is what we did in the first video, where we really just used Lua as an elaborate configuration file. Once everything's been loaded in, it's all left to the C++ to deal with. For my application, I'm going to aim for a nice happy medium. The bulk of the hard work is going to happen in C++. So yes, we're going to handle input, we're going to handle object behaviors and physics and collisions and all that sort of thing. and the rendering. And I'm going to use Lua to define our world, but also, and we're getting to the crux of this video, to automate it. Automation could involve things like cut sequences, or moving platforms. How about object AI, or simply game world interactions? Approaching things this way means all of the complex mathematics and the real CPU intensive stuff is being done by the C++ program. And very occasionally we dip into the Lua program to get some sort of update on how the C++ side of things should behave. In my Code It Yourself role-playing game series, I did a similar thing, but I did all of this world automation in C++ itself. We used a reasonably trivial set of object-oriented programming principles to handle these interactions between objects. It was a bit like scripting, but using the C++ program to facilitate that scripting. Therefore, if we did make slight changes to the sequence of events that happened, let's say a character walks to the top of the screen and turns left, but we want to change it to turn right, we still have to recompile the whole program. But this did allow us to have quite elaborate scenes, which at the time I claimed to be some sort of theatre engine. So just to reiterate, all of the really tight loop stuff is being done in C++. We'll generate a series of events at certain stages of our C++ algorithm, which will require Lua to provide some sort of information in response to that event. And what we'll see is that Lua has one particular trick up its sleeve, which as at this moment C++ doesn't provide, though I think it will in the future, and that is the use of coroutines, which are great for automating stuff. So let's start building this up. Right now, our world is fairly static. It consists of a background being rendered of solid or not tiles. Things that move or things that are interactable within the game world I'm going to call dynamic objects. And for the purposes of this video, I'm going to simply define a dynamic object as a structure that has a position in the game world, something that describes its size, potentially a velocity, an ID which defines what it looks like, and a flag which tells us whether the dynamic object should be removed from the world or not. And I'm going to store all of the dynamic objects that are created in a vector of dynamic objects as, get this, shared pointers. Not something we see very often on the One Learn Coder channel, but we'll also see are not very easy to use with Lua, and we may see in part 3 of this series a slight change in this regard, but for now this will work just fine. It's going to be possible for the Lua script to create a various number of dynamic objects. So I'm going to create a createDynamicObject function, which takes in what is the type of the object and a position in space. All this function does is create the dynamic object, set its ID and its position, and pushes the object into the vector. Finally, it returns the shared pointer. Naturally, if we want Lua to call this function, we need to wrap it. So we'll wrap it in a static function called wrapCreateDynamicObject. You see the pattern here? We'll extract the parameters sent with this function, the type and the position, and this function is actually going to return back to Lua the value of the pointer that's been created. So in Lua we will have some sort of unique identifier for that object. I don't need to specify a index as such, 0, 1, 2, 3, or 4, I can just use the pointer itself. And so unlike the other functions that we've created so far, I need to push something back to the Lua virtual machine. In this case, push light user data, it's a pointer, to the Lua state that was supplied with this function, and here I'm calling the createDynamicObject function, specifically accessing the raw pointer underneath the shared pointer. And you can see where this might get a little bit messy later on, but for this simple video it's going to suffice. I need to return 1 to tell the Lua virtual machine that this call is going to return one item of data. In this case, it's our pointer. And as usual, I will expose this createDynamicObject function to the Lua script. In the Pixel Game Engine's onUserUpdate function, once we've drawn the level, I'm then going to draw the dynamic objects on top of it, which is just a case of iterating through the vector of dynamic objects and choosing an appropriate sprite for the type ID that we've specified in the dynamic object structure. Going back to Lua, at the end of our level construction function, I can call the createDynamicObject function, passing in the type and the position in the game world. This function will return an identifier for that particular dynamic object, and I'm going to store that in a player object variable. So let's just take a quick look. So here we can see the scene as before, but now we've got a new object, which looks a bit like Marty McFly from Back to the Future, floating in space. Since this is the player object, I might want the user to be able to control it. And one of the advantages we have here is that a dynamic object is just a dynamic object. Potentially, the player could control any dynamic object in the game. So I'm going to create another function, assign player control, which takes in the unique identifier and will allow us to control that in the C++ program. Because the player can only control one object at a time, I'm going to create another shared pointer specifically that points to the object that we're deciding should be under player control. And to our class, it's time to allocate another pair of functions. The first one, simply assign player control, which takes in a raw pointer to a dynamic object. Now, this is where things get a little bit complicated because we've used smart pointers. When the smart pointer went out to Lua, it went out as a raw pointer, up here, this .get. When Lua is returning that pointer, well, there's no smart pointer wrapped around it. So I want to find the corresponding smart pointer I have in my vector of dynamic objects, which represents that specific area of memory. This is a hack and can be improved, but it is necessary to do it this way for now. It may be very tempting to say, well, just wrap up this pointer in a new smart pointer, but there'll only be one instance of that particular smart pointer, and so when it goes out of scope, it will delete the object it's pointing to, even though existing smart pointers are already pointing to that data. It goes without saying, had I chosen not to use smart pointers in this instance, life would be much simpler. And it also makes an argument for perhaps not using the pointer value itself as a unique identifier, but rather some sort of index. However, we'll see what happens with all of that in part 3. I'll need to wrap this function as usual. In this case, I'm getting the host object again, and I'm getting the raw pointer value, which is the only argument we're specifying as part of our automation script here, assign player control, the host, and the player object. I'll expose this function to our script, but I also now need to implement the control for that object. And this is very simple right now. For this video, we're not worrying about collision detection at all. We're just going to move the object around the screen using the W, S, A, and D keys by setting the velocity value of that dynamic object and updating its position accordingly, modulated by f-elapsed time. This is the sort of stuff we've done thousands of times now. So let's take a look. There's our object, and as I hold down the keys, I can move the object around in the scene. But let's just quickly prove a point. In my external script, I've now created another player object. And so without any recompilation of the C program, I'm just going to run the script. And we can see there are now 2 objects, and the second one is under player control. We've made a significant world and behavioral change without modifying the source program. We're now starting to see the very starting stages of how Lua is configuring a background game engine.
But this video is about automating things that are not under player control, and instead will allow the C++ environment to manipulate the objects under the guidance and supervision of the Lua script.
I'm going to make a fundamental assumption at this point, that any dynamic object in the game can be controlled automatically. And this is one of those situations where we need to decide on a balance between what the game engine can provide and what Lua is capable of implementing for us. I'm going to implement a base structure called a manipulator. As you can see, it's abstract due to the presence of this pure virtual function. The manipulator simply points to a particular dynamic object, can update it somehow, and signals when it has finished the manipulation. I will derive from this base class various different types of manipulator that implement different types of motion in the game. And we'll see it doesn't have to be restricted to motion either. So let's assume I want one type of manipulator that linearly interpolates the object from a starting position to an ending position. I'll call this moveObject. And it will have some fields that represent the starting position and the target position. I also want this motion to take a specific amount of time, which will be specified. And so I'll also want to keep track of how far into this motion have I got so far. The constructor for this manipulator takes in a pointer to the object, the target location, and the time it needs to pass to get there. And we'll see that the starting position of this manipulation is the object's current position. The update function will be called by C++ every frame. The first thing I'll do is accumulate how much time has passed. F-elapsed time is the time between 2 successive frames. and I will explicitly set the dynamics object's position by taking the difference of the target and the start position, multiplying that by normalized time, so in this case this will yield a value between 0 and 1, and offset it by the starting position. This is a two-dimensional linear interpolation, nothing more. And I talked about this in my Essential Mathematics for Game Dev video. If the time that's passed so far is greater than or equal to the time we expected the motion to take, then I'm going to clamp the dynamic object's position at the end location, the target position, and set the flag completed to true. By default, this flag is false. My update function will return the value of this flag. I'll also add to my class 2 more vectors, both of shared pointers to type manipulator. This one, vManipulators, contains the manipulators currently in effect this frame. Curiously, I'm also creating a vector called vNewManipulators, and we'll see why in a moment. In onUserUpdate, before we do any player control, I'm going to update all of my active manipulators, and I'll do that with a little auto for loop. Using polymorphism, I'll call the update function, and if that returns true, that means this manipulation has completed. And it's at this point that we now need to dip into Lua and start looking at how we structure things there. In my Lua script, I'm going to define an empty table called dynamics. And for now, I'm going to leave the player object 1 in, but I'm going to remove player object 2. I want to add a moving platform to the game. So I'll call the create dynamic object and specify the type, which in this case 2 is moving platform, and the starting position. But I want this particular moving platform to follow a certain path. And this is where we're going to start using Lua Coroutines. This function, dynamic behavior 1, is going to be unique for this platform and specify the path the platform should take. I never want it to stop, so the first thing I'll do is create a while loop. So the platform is basically going to move around 4 different locations around the screen. To move it to a location, we'll need to create a function called moveObject in our C++ program and call it from here. And I want it to move from that location, to this 3rd location, and this 4th location. These are the coordinates, and this is the time I want it to take. So it'll take 5 seconds to move each time. But at the moment you may see a bit of a problem here. If anything calls this function, it never ends. It's a while true loop. It will just continuously keep calling these functions in our host program. This is not a good thing. Coroutines allow us to do something a little bit strange to us C++ developers. And that is, we can abort the function at a particular point, but we can come back to it at that point later on. So I want to sit in this loop, and I want it to start moving the platform to that location. The C++ program is going to go away and move it, but I don't want to start issuing more moves in the background. I want to wait until the C++ program signals, well, that object has arrived at that location. And a coroutine will allow me to do just that. I can yield, which means it'll execute this line, it'll execute this line, and then it'll stop here until it is signaled to continue. Naturally, I'll want to do this for all of my movements. Now, the cool thing about a coroutine is even though this is yielded, I can still call and run other parts of the Lua code. In many ways, you can think of this as a thread, though I will emphasize it isn't a thread. Now I've created a unique function that represents the behavior of that dynamic object. I want to associate that behavior with the moving block dynamic object we created earlier. And this is one of the most beautiful parts of Lua. In my dynamics table, I can index it with the unique identifier of our moving block and specify a particular property called behavior to represent what is effectively a function pointer to a coroutine that's been created based on our dynamic behavior 1 function. And I'll demonstrate later that it is now trivial to associate different behaviors with different objects or the same object or change the behavior of an object. When you call coroutine create, it doesn't actually run the function straight away. All it has done is created the coroutine. We need to start the coroutine. And to do that, I'm going to create a Lua function called issueNextTask. Note the lack of an underscore at the start. This is going to be something we implement in Lua. And I'm passing to this function our pointer to our host environment as always, but also the pointer to the dynamic object. So let's create this issueNextTask function here. The first thing I'll check for is if the coroutine is dead or not. A coroutine that's dead is one that has managed to exit the function. In this case, our dynamic behavior 1 function can't ever exit, so the coroutine's status is never going to be dead. But that doesn't mean we can't have something which is only executed once, for example. And this is the important line of code. Coroutine.resume. And we pass in our function pointer to the behavior that we've associated currently with that dynamic object, and we also pass in the 2 arguments to the function. So let's just compile this in our minds for the time being. We're creating a dynamic object, and we're telling it to follow the behavior defined by coroutine dynamic behavior 1. And then we call the issueNextTask function. The issueNextTask function makes sure that the coroutine actually exists, and then it calls the coroutine.resume function. Now, the first time you call that on a coroutine, it effectively starts the function. So it'll hit this while true do, which will then call this move object in our C++ environment, and then it will yield. At this point, Lua has finished. It will stop there. Once the movement has finished in our C++ program, i.e. the manipulator has finished moving the dynamic object, we can call this issueNextTask function again. The coroutine gets resumed, but because the coroutine is already running, it resumes from the point that it was last yielded. So we run this line and then wait again, and we'll keep doing this in a loop. So now we need our manipulator in C++ to call issueNextTask once that manipulation has completed. This is simply a case of finding the function and calling it, and all we're going to push to the function is the this object again, as we did before, and we're also pushing the pointer to the dynamic object. It's important to push that pointer because that pointer is used as an index into our dynamics table so it can get the correct coroutine, i.e. we're going to reuse this function for all of the objects in our game. This is really convenient, and this is one of the really nice things about Lua being as flexible as it is. Because everything is stored as key value pairs, you can do lots of interesting tricks, such as storing functions as properties of other objects. So in C++, when we're updating our manipulators, for most of the time they're doing the hard work, positioning the object in the right location, and Lua isn't doing anything at all. It's just sitting there waiting now for a call to issueNextTask, which may only happen once every 100 or 1000 frames or so. It's not a very common occurrence, so we've kept our Lua overhead down and made sure that C++ is doing the hard bit. The policy we've decided upon is that our manipulators do a simple amount of movement at a time. So when that manipulation is complete, I want to remove that manipulator from our vector of manipulators, which I'm doing using the eraseIf function of the standard library, which just checks to see if the complete flag has been set. Now, here's an interesting thing. When we call the issueNextTask in our Lua script, that will call potentially move object or various things which will generate new manipulators. We can't push those new manipulators directly into this vector of manipulators because we're iterating through this loop, and we don't want to change the container we're currently iterating through. That can lead to some really nasty things happening. So any new manipulators that are generated as a result of calling issueNextTask, we will place into our vector of new manipulators. And each frame I'm going to copy that vector over into our active manipulator vector, and indeed clear it. So now we need to implement this moveObject function. And as before, it's a pair of functions. The first one is moveObject, which takes the object, the location to move it to, and the amount of time we want it to take, and we place that at the back of our new manipulators vector. And you'll see here it's all in one line. I'm creating a shared pointer to the manipulation object. In this case, it's a type manipMoveObject, and we pass in the relevant data. And I'll want to wrap that as well. Usual stuff, get the appropriate pointers, get the information we want to pass to the function, and ultimately call our function. And finally, expose the moveObject function to our Lua script. So let's take a look and then analyze to see if it's working properly. So we can see a dynamic object has been created. It looks like a moving platform, and the moving platform is following a path automatically around our scene. We assigned player control to the player, so I can move the player around, and in the background our moving platform is quite happily doing its own thing. So it seems on the surface everything is working just fine. But I just want to prove that Lua isn't indeed always computing things. And to demonstrate this, in my loop here, I'm going to use Lua's print function, start of circular motion. And in the issue next task function, I'm going to print next task issued. Now the nice thing about Lua and the console, and indeed the Pixel game engine having a console in the background, is we can actually see these outputs from Lua whilst our program is running. So notice again, no compile time, that's the beauty of external scripting. And we can see that next task issued is called very infrequently, only when the manipulation has finished, i.e. the platform has gotten to that target location. And once it's finished its loop of 4, next task issued, start of circular motion. So here Lua is controlling for us quite a complicated sequence of events, but it's barely being invoked by the host application. This is a great scenario because it means C++ is doing the hard work and Lua isn't. And as you start developing applications such as this, you'll find yourself operating more and more in the scripting language domain rather than the C++ language domain. So let's add another moving platform without touching any of the C++ at all. This time I'm going to add moving platform 2, give it a start location, and I'm going to create a new dynamic behavior function specifically for this platform. This is just going to be a platform that moves up and down. Let's take a look. So now we've got 2 moving platforms. One just moves up and down, one's moving around in a circular motion. Again, we can see Lua isn't doing very much at all in the background. We didn't change our C++ program, but we've changed the element and nature of the game. And of course these automations can be tweaked and customized as necessary. So this command was moving the platform up in 4 seconds, maybe I want it to fall back down in 1 second. Without any recompilation, it goes up, and it falls back down very rapidly. There's no collision detection yet, that's coming in part 3, which we'll see we'll also use to implement various triggers to cause other things to happen. But let's add a slightly more complicated motion. In fact, I'm going to add 2 more. The first one is actually very simple. Teleport object. It doesn't move anything at all, it just immediately positions a dynamic object at a set location. So this specific manipulator doesn't live for a very long time. This next manipulator is going to move the objects given a curved path. And it's just going to be a simple Bezier spline. So you specify a starting location, which is where the object currently is, some sort of waypoint, it doesn't go through it, but it biases it towards it, and a target location. And again, as before, a time too. You'll actually see it's very similar to how we did things before, except this time I'm using the spline equation instead. And I have a video just about splines. It doesn't cover Bezier splines, but it'll give you an idea about how this works. It's effectively a non-linear interpolation. But other than that, it's exactly the same as our linear interpolated movement. Naturally, these new manipulators are going to require new functions. So here are the functions for the teleport object, and here are the functions for the move object with curvature. You may decide in your interface not to have lots of individual functions, but to have one, which is customized accordingly in Lua. And I thought it would be nice to just finish the video off with a simple example of how you can customize a behavior which might be used as part of a tutorial or something like that. I'm going to create a behavior called run and jump. And since I'm just demonstrating it, I'm going to keep this in a while loop as well. Don't forget, these don't necessarily have to be kept in while loops, they can be just fire and forget behaviors. Once the coroutine has died, there's nothing else for it to do. The dynamic object will just exist in that location until it's instructed to do something else, either by the host application or by some other function in the script. But just keeping them repeated makes it easy to debug them. The first thing I'll do is teleport the object to a specific location, and then I'll yield. I'm then going to do 3 movements. One moves the object linearly, then we're going to move the object with a curve, and then we're going to move the object linearly again. Down where we're creating dynamic objects, I'll create one called Player Buddy and associate it with this run and jump behavior. Let's take a look. So now we can see the other player object, or potential player object, is running, jumping, and landing. It's quite an elaborate cut sequence. And in the background, our platforms are still moving and we still have player control. Once you've established a set of basic manipulations for the dynamic objects, you could create quite elaborate sequences. You could also have the sequence behavior functions operate based on conditional information. And we'll look at all of that in part 3.
And so that's that. It's early days yet in this project, but I'm hoping you're beginning to see the benefits of using a language like Lua as an external scripting language for your projects. If you've enjoyed this video, please give me a big thumbs up, have a think about subscribing, come and have a chat on the Discord server. All of the source code for this video will be uploaded to the GitHub, and I'll see you next time. Take care.